At 0100 hours, 1940, Sergeant James Miller sat in the rear turret of a Wellington bomber, watching German searchlights sweep the sky over Berlin. He was 19 years old, freezing cold and terrified. The Wellington was Britain's pride, a twin-engine bomber with an aluminum frame covered in fabric, making it sturdy, reliable, and hopelessly slow. As the aircraft plodded through darkness at 180 miles per hour, Miller felt trapped in a flying coffin. The German anti-aircraft guns below didn't have to work hard. They simply put up a wall of steel in front of the slow-moving British planes and waited. A German Me-110 night fighter slid in behind them. Miller gripped his Browning machine guns, knowing his 4.33 caliber weapons were useless against the cannons of a German fighter. He shouted a warning, but too late. Cannon shells hammered into the Wellington's fuselage, ripping the fabric skin apart like cheap. The aluminum frame twisted. The starboard engine caught fire, turning the bomber into a burning beacon. The Wellington rolled over and began its long dive toward Earth. It wasn't a fight. It was slaughter. This was the reality of Britain's air war in 1940. Doctrine promised that bombers would always get through if they had enough guns, so they built flying fortresses, bristling with turrets, ammunition crates, and armored plating. The theory said if you mounted enough machine guns, enemy fighters would stay away. Physics told a different story. All those guns and turrets added massive weight. Weight meant drag. Drag meant slow. In a sky filled with agile 300-mile-per-hour German fighters, slow bombers were just targets. The Royal Air Force was losing crews faster than they could train replacements, bleeding out in the cold night air over Germany. The crisis deepened beyond just combat losses. Britain was running out of aluminum. Factories were consuming the metal at an impossible rate. Every Spitfire required 6,800 pounds of strategic material. Every Lancaster bomber 22,000 pounds. The bauxite mines couldn't keep pace with demand. Convoys bringing ore from America were getting torpedoed by German submarines in the Atlantic. The Air Ministry faced a nightmare. They had trained pilots but were running out of raw materials to build aircraft. Production managers stared at projections showing factories going silent within months because there would be nothing left to melt down. In November 1940, a man named walked into the Air Ministry with a solution that sounded insane. Was an aviation legend who thought like an engineer, not a soldier. He looked at the heavy, lumbering bombers and saw a fundamental mistake in their design philosophy. He proposed a radical alternative: build a bomber that didn't fight back. No defensive guns, no armor plating, no rear gunners, just 2 crew members, 2 massive engines, and speed. Pure, overwhelming speed. The concept was mathematical. Explained the physics to skeptical Air Ministry officials. A Wellington bomber weighed 18,500 pounds empty. Add 4,000 pounds of guns, turrets, ammunition, and armor. Total weight, 24,000 pounds. His proposed design would weigh 12,000 pounds, half as much. Both aircraft would use the same Rolls-Royce Merlin engines producing 1,620 horsepower each. But the physics of power-to-weight ratio meant everything. The Wellington's engines moved 14.8 pounds per horsepower. His design would move 7.4 pounds per horsepower. Every horsepower would push half the weight. In aerodynamics, that difference translated directly to speed. The Wellington cruised at 180 miles per hour when loaded with bombs and ammunition. Calculations showed his design would cruise at over 300 miles per hour, possibly 350 or more. The German Me-109 fighter maxed out at 390 miles per hour in level flight. An unarmed bomber cruising at 380 miles per hour would be functionally untouchable. Speed would become the only armor necessary. If enemy fighters couldn't catch you, defensive guns were irrelevant. If you were too fast to hit, armor was just dead weight slowing you down. The generals called it suicide. They predicted the first German fighter that spotted this defenseless aircraft would shred it, but had a second innovation that made them think he'd completely lost his mind. He wouldn't build it from scarce aluminum, he'd build it from wood. The room went silent. Wood was for furniture in First World War biplanes, not modern combat aircraft. But logic was sound. Britain was running out of metal but had unlimited forests. He proposed using Canadian Sitka spruce for structural frames, birch plywood for skins, and Ecuadorian balsa for core material. Wood was lighter than aluminum per unit of structural strength. The construction method would create a smooth monocoque shell, two fuselage halves layered over concrete molds, glued with resin adhesive and clamped together. No rivets, no overlapping metal sheets. The result would be a surface smoother than any metal aircraft, reducing drag even further. The Air Ministry experts mocked him. They called the project Freeman's Folly and nicknamed the proposed aircraft the Termite Hotel. They predicted it would rot in rain, the glue would fail in tropical heat, and it would burn like a torch if hit. But Air Chief Marshal Freeman saw the desperation of Britain's situation and secured funding. Because metal factories were overwhelmed, production was outsourced to an unlikely workforce. Furniture makers, piano factories, and church pew carvers received blueprints for a high-performance bomber. On November 25, 1940, the prototype took flight from a cold, damp airfield. Test pilots had been skeptical, tapping the fuselage and hearing hollow wood instead of reassuring metal. But Junior climbed into the cockpit and fired up the twin 12-cylinder Merlin engines. The wooden aircraft accelerated down the runway with shocking violence, tearing into the air and climbing like a rocket. Leveled off and pushed the throttles forward. The airspeed indicator climbed 300 miles per hour, then 350, then 400. Officials on the ground tapped their stopwatches in disbelief. The wooden aircraft, the one they'd called the Termite Hotel, flew faster than the Spitfire fighter, faster than the German Me-109. The laughter stopped instantly. The test flight proved the mathematics correct. Physics worked exactly as had calculated. But speed demonstrated on a clear afternoon over England didn't convince the old guard at the Air Ministry. They still believed a German 20mm cannon shell would shatter the plywood and tear the airframe apart. They worried the glue would fail in extreme temperatures. Despite their doubts, desperation forced a decision. The Royal Air Force needed bombers that could survive. In late 1941, the first production aircraft, officially designated the Mosquito, were delivered to operational squadrons. The real test would come not in controlled flight tests, but in combat over occupied Europe. The first operational Mosquitoes arrived at Royal Air Force in late 1941. Number 105 Squadron received the initial batch of aircraft, and the crews walking out to see them were deeply skeptical. They'd heard the stories, a bomber made of wood with no guns. The smooth wooden shapes sitting on the tarmac looked nothing like the heavy, reassuring metal bombers they were accustomed to. Pilots climbed into cramped cockpits that smelled of wood varnish and aviation fuel. There were no gun turrets to inspect, no defensive positions to check. Just two seats, a bomb bay, and those twin Merlin engines. The skepticism vanished the moment they pushed the throttles forward. The Mosquito didn't lumber into the air like the Wellington or Lancaster. It leaped off the runway and climbed with the aggressive angle of a fighter aircraft. Crews who'd spent years nursing heavy bombers through the sky suddenly found themselves flying something that responded like a sports car. Over the English Channel on their first training flights, pilots discovered the performance numbers weren't optimistic estimates, they were conservative. The wooden aircraft cruised comfortably at 320 miles per hour. When they needed speed, it would push past 380. At that velocity, German fighters had to work to catch them, and catching them meant nothing if the Mosquito pilots saw them coming and accelerated. The first combat mission came in spring 1942. A daylight raid on a German industrial target in occupied France. Traditional doctrine said daylight bombing without fighter escort was suicide. German Me-109s and 190s would tear unescorted bombers apart. But the Mosquito crews had speed on their side. They went in fast and low, using terrain to mask their approach. German radar picked them up, fighters scrambled, but by the time German aircraft reached intercept positions, the Mosquitoes were already over the target. Bombs away. Turn for home. German fighters pursued, pushing their engines to maximum power, but the wooden bombers pulled away. The Mosquitoes landed back in England with no losses, no damage, and bomber crews talking in amazed tones about how they'd simply outrun the opposition. German intelligence began receiving troubling reports from sector commanders in France. April, British twin-engine bomber, type unknown, evaded 4 Me-109s in pursuit. May, same aircraft type, 6 encounters, 0 successful intercepts. June, 8 reported sightings, German fighters unable to close to firing range. Intelligence officers in Berlin analyzed the data with growing frustration. Photo reconnaissance eventually captured images of the aircraft on British airfields. Analysts measured dimensions, identified the twin Merlin engines, and calculated performance. Their conclusion seemed impossible. The British had built a bomber faster than their own fighters using the same engines installed in standard Spitfires. German Tactical Command issued new intercept procedures. Station fighters at higher altitudes to dive on the British bombers, converting altitude to speed advantage. Position aircraft in ambush patterns instead of reacting to radar warnings. Increase patrol density to improve intercept probability. The countermeasures failed. The Mosquitoes continued appearing over targets, striking and vanishing before German fighters could engage effectively. When German aircraft did achieve firing positions, the wooden bombers would simply accelerate away. Pilots reported the same frustrating experience. Visual contact achieved, optimal attack angle established, throttle to maximum power, target pulls ahead anyway. The Royal Air Force began expanding Mosquito operations. Squadron 105's success led to more units converting from heavy bombers. Crews volunteered eagerly for Mosquito squadrons once they understood what the aircraft could do. The missions grew increasingly bold. Precision strikes on factories, bridges, and rail junctions that would have required dozens of heavy bombers could be accomplished by 4 or 6 Mosquitoes. Casualty rates told the story most clearly. Lancaster and Wellington squadrons lost 5 to 8% of aircraft per mission on average. Mosquito squadrons, less than 1%. Crews calculated their odds quickly. 30 missions in a Lancaster meant almost certain death or capture. 30 missions in a Mosquito meant you'd probably survive the war. By summer 1942, the pattern was established across the European theater. German sector commanders learned to dread the Mosquito raids. The aircraft appeared without warning, struck with precision, and disappeared before effective response could be organized. Anti-aircraft artillery proved useless. The wooden bombers flew too fast and too low for gun crews to track effectively. Fighter patrols couldn't maintain the constant coverage necessary to intercept targets traveling at nearly 400 miles per hour. German intelligence analysts studied every piece of available data searching for vulnerabilities. They found none. The basic mathematics of the situation were unbeatable. Same engines, half the weight, resulted in speed no Doctrine could counter. The Mosquito evolved beyond simple bombing missions. Photo reconnaissance versions carried cameras instead of bombs, flying deep over German territory to photograph installations, troop movements, and industrial sites. The speed that kept bomber variants safe made reconnaissance Mosquitoes nearly invulnerable. They could penetrate defended airspace that would be suicidal for conventional reconnaissance aircraft, photograph targets at leisure, and return before German fighters could respond. Intelligence officers in London received crystal-clear images of targets hundreds of miles inside German-occupied territory, delivered by crews who treated the missions almost casually. Night operations added another dimension. The Mosquito's speed remained effective in darkness. German night fighters relied on radar to locate British bombers, then closed for visual identification and attack. Against slow Lancasters and Wellingtons, the tactic worked devastatingly well. Against Mosquitoes, it failed. Even when German radar operators successfully vectored night fighters toward the wooden bombers, the closing speed was too high for effective attacks. By the time a German pilot achieved visual contact and prepared to fire, the Mosquito was already accelerating away into darkness. German High Command recognized they faced a fundamental problem. The British had discovered a solution to bomber vulnerability that German Doctrine couldn't counter. Every defensive measure failed for the same reason: the basic physics of power-to-weight ratio. German engineers examined captured Spitfire engines, identical Merlins to those powering Mosquitoes, and found no secret modifications. The speed advantage came entirely from weight reduction. Building bombers light enough to outrun fighters required eliminating defensive armament and using lighter construction materials. But German industrial capacity was built around metal aircraft production. Shifting to wooden construction would require retooling entire factories during a war where production tempo was already stretched to breaking point. By autumn 1942, the Mosquito had validated every aspect of its design philosophy. Speed did provide better protection than armor. Eliminating guns did produce enough weight savings to transform bomber survivability. Wooden construction did work in combat conditions. The aircraft the experts had mocked, as the Termite Hotel was rewriting tactical doctrine across the European theater. But the ultimate test of the Mosquito's capabilities still lay ahead. A mission so difficult that only the wooden bomber's unique combination of speed, agility, and precision could possibly succeed. By early 1944, the Mosquito's reputation was established, but the aircraft faced its most challenging mission on February 18th. Amiens prison in northern France held 120 French resistance fighters scheduled for execution within 48 hours. British intelligence identified the prisoners as critical assets, sabotage coordinators, network leaders, intelligence operatives whose loss would cripple resistance operations across 3 regions. The prison sat in the middle of the city with walls 3 feet thick. Conventional heavy bombers couldn't achieve the surgical precision required. Collateral damage would kill hundreds of French civilians. Only the Mosquito had the combination of speed, low-altitude capability, and precision necessary to attempt the mission. Group Captain Charles assembled 19 Mosquitoes at Royal Air Force on the morning of February 18th. The briefing was stark. First wave would breach the outer walls using skip bombing technique, releasing 500-pound bombs with 11-second delay fuses that would skip across frozen ground and detonate against the wall base. Second wave would strike the main building to blow cell doors without collapsing the structure. Third wave would remain in reserve, attacking only if the first 2 waves failed. Timing had to be exact. Attack at noon when guards were at lunch, prisoners in cells, staff minimal. Weather forecast: freezing rain, poor visibility, wind gusting to 30 knots. Conditions that would ground any other bomber force. At 11:57, led the formation across the English Channel at wave-top height to avoid German radar. They climbed to 250 feet for the attack run. The weather was worse than forecast. Freezing rain coated windscreens. Visibility dropped below half a mile. Wind buffeted the wooden airframes. Traditional doctrine said abort under these conditions. Pressed on. At exactly noon, the fortress-like prison appeared through the mist. Signaled the attack, and the first wave lined up for their bombing runs. The skip bombing technique required nerve. Pilots descended to 50 feet, released bombs that bounced off frozen ground, then pulled up hard to clear the blast zone. The 11-second fuses gave just enough time. Explosions disintegrated the massive stone walls, creating gaping holes 30 feet wide. The second wave faced harder work, flying through smoke and debris to hit the main building with surgical precision. Their bombs had to blow cell doors without bringing down the roof and killing everyone inside. The pilots threaded their aircraft through smoke at 200 feet, released at exact calculated points, and climbed away as explosions ripped through the prison structure. Inside, the first blasts threw prisoners and guards to the floor. When cell doors were blown off hinges and outer walls collapsed, prisoners realized what was happening. It was a rescue. Panic transformed into a desperate rush for freedom. Over 250 men poured through the breached walls, scrambling over rubble while confused German guards fired wildly. Group captains circled above, confirming the breach and the escape before signaling the reserve wave to turn back. The mission was successful, but made a fatal decision. He climbed to 2,000 feet to assess damage, lifting himself out of the protective ground clutter. A patrol of German 190 fighters spotted his silhouette against the clouds and dove. Cannon shells hammered his Mosquito until the wooden tail section shattered. The aircraft crashed, killing and his navigator instantly. The surviving Mosquitoes raced back to England, battered and from anti-aircraft fire and debris. They landed at to wait for their leader who would never return. The mission cost 3 aircraft and 6 crew members, but 250 French resistance fighters escaped to continue their work. The raid also killed 50 German guards and, tragically, over 100 prisoners who died in the bombing, the price they had been willing to pay for a chance at freedom. The Amiens raid proved definitively that only the Mosquito could execute missions requiring this combination of speed, precision, and low-altitude capability. The psychological impact on German forces was immediate and severe. The raid demonstrated that no target was safe. no matter how deep inside occupied territory or how well defended. German secret police began moving high-value prisoners at night to hide from the wooden bombers. Intelligence files showed the fear spreading through occupation forces. If the British could breach a fortress prison in broad daylight under terrible weather, what couldn't they strike? As spring turned to summer 1944, the Mosquito faced a new threat. German V-1 flying bombs began hitting London, pilotless cruise missiles carrying 1-ton warheads at 400 miles per hour. Conventional fighters struggled to intercept them. The V-1 flew too fast for most aircraft and too low for high-altitude interceptors. Shooting them down over populated areas just detonated the warhead early, causing the destruction they were meant to prevent. The Mosquito became the primary hunter, because only its speed allowed pilots to chase the missiles effectively. Crews developed an extraordinary tactic: dive at terminal velocity until the wooden airframe shook and structural members groaned, close within feet of the pulse jet's hot exhaust. Match speed precisely at 400 miles per hour. Then use the airflow over the wing to physically flip the V-1 over, disrupting its flight and sending it tumbling into empty fields. The maneuver required surgical precision at extreme speed in an aircraft built primarily from wood and glue. Mosquito pilots destroyed dozens of V-1s this way, saving countless London civilians. Late 1944 brought the ultimate test. Germany unveiled the Me-262, a twin-jet fighter capable of 540 miles per hour. On paper, the jet should have rendered every propeller-driven aircraft obsolete, including the Mosquito. The Me-262 was 160 miles per hour faster in straight-line flight. German pilots expected easy victories. Reality proved different. In combat, the Mosquito's agility compensated for its speed disadvantage. The jet engines took time to spool up. The Me-262's turn radius was wide. High speed made precise aiming difficult. Mosquito pilots learned to exploit these weaknesses. They would bait jets into turning fights, using turn radius to stay inside the Germans' arc. The wooden bomber could outturn the jet at combat speeds. German pilots found themselves frustrated, unable to achieve firing solutions against targets they could theoretically outrun by massive margins. Combat wasn't a drag race measured in straight-line speed. It was angles, energy management, and pilot skill. Aircraft built by furniture makers were surviving encounters, with jets representing the cutting edge of aviation technology. When the war ended in May 1945, the Mosquito had flown every imaginable mission type: strategic bombing, tactical strikes, photo reconnaissance, night fighting, anti-shipping operations, pathfinding for heavy bomber streams, submarine hunting. The critics who had mocked this wooden bomber were now scrambling to acquire the design. Air forces worldwide wanted to study how Britain had achieved this level of performance. Seemingly insane proposal had been vindicated completely. Speed had proven better protection than armor. Wooden construction had worked in every theater and climate. The mathematics of power-to-weight ratio had defeated conventional wisdom about bomber design. But the arrival of the jet age meant the Mosquito's time was ending. New all-metal jet fighters like the Meteor and Vampire represented the future. The Wooden Wonder, despite its extraordinary combat record, was a wartime solution built on wartime constraints. As peace returned to Europe, the aircraft that had been too valuable to lose during combat became too troublesome to preserve during peace. The end of the war brought an unexpected fate for the Mosquito. The aircraft that had been too valuable to lose during combat became too problematic to preserve during peace. Wooden construction that had been an advantage during wartime aluminum shortages became a liability in peacetime storage. Wood rotted. Glue degraded over time. The airframes required constant climate control and maintenance that air forces and museums couldn't afford. Unlike all-metal aircraft like Spitfires and Lancasters that could sit in storage yards for decades, Mosquitoes had a shelf life measured in years without proper care. The solution was brutally pragmatic. Across Britain, hundreds of Mosquitoes were dragged to the edges of airfields. Ground crews stripped them of instruments, engines, and anything valuable. Then they set them on fire. The plywood that had survived German cannon fire and outrun jet fighters burned fiercely. Birch ply and balsa core turned to ash within hours. The The wooden wonder that had humiliated the German Air Force disappeared as quickly and silently as it had arrived, consumed by flames at the very airfields where it had proven everyone wrong. The destruction was systematic. 7,781 Mosquitoes were built during the war across multiple production facilities. By 1950, fewer than 50 remained intact. The mathematics of preservation economics were harsh. A metal Spitfire required minimal maintenance to survive storage, occasional inspections, basic corrosion prevention. A wooden Mosquito required controlled humidity, regular structural checks, ongoing treatment for wood degradation. Museums and air forces making decisions about which aircraft to preserve chose metal over wood. The decision was practical but historically devastating. Today, only 30 Mosquitoes survive worldwide. They sit in museums looking fragile and organic compared to the metal warbirds surrounding them. Visitors approach expecting the familiar ring of aluminum when they tap the fuselage. Instead, they hear a dull, hollow resonance, the sound of layered wood. The shock is visible on faces. This beat the German Air Force. This wooden aircraft outran jets. This thing built by furniture makers dominated the European skies. The disconnect between appearance and achievement is profound. The statistics tell the story the surviving aircraft barely can. 7,781 built. 0 lost to structural failure. Not one Mosquito came apart because wood couldn't handle combat stress. Not one failed because glue dissolved or plywood shattered under G-forces. The experts who predicted rot, fire, and catastrophic structural failure were wrong about every prediction, was right about every calculation. The wooden construction that seemed insane in 1940 proved more reliable than anyone imagined possible. The loss rates provide even starker evidence. Between 1942 and 1945, Royal Air Force heavy bomber crews faced brutal mathematics. Lancaster squadrons lost an average of 5 to 8% of aircraft per mission. 30 missions meant near-certain death or capture for crews. The odds were openly discussed. Bomber crew life expectancy was measured in weeks, not months. Mosquito squadrons told a completely different story. Loss rate, 0.3%. 99.7% of aircraft returned from missions. The difference wasn't luck or courage. It was physics. 12,000 pounds moved by 3,240 horsepower survived exponentially better than 24,000 pounds moved by the same total power. The doctrine changes came swiftly once the war ended. By June 1945, air forces worldwide were studying the Mosquito's success and rewriting tactical manuals. The principle was clear. Speed and altitude provided better protection than defensive armament for strike aircraft. The United States Army Air Force revised bomber doctrine to emphasize performance over defensive capability. The concept of the fast, unarmed bomber influenced jet aircraft design for decades. Modern strike aircraft from the English Electric Canberra to the F-111 followed the Mosquito's philosophy. Use speed and electronic countermeasures for protection, not guns and armor. German Air Force analysis after the war revealed how completely the Mosquito had overturned their defensive doctrine. Intelligence files showed hundreds of frustrated reports from pilots and commanders who couldn't counter the wooden bomber. Post-war interviews with German fighter pilots revealed the psychological impact. They described the Mosquito as the most frustrating opponent, visible on radar, occasionally spotted visually, but impossible to catch. Pilots reported seeing Mosquitoes, achieving optimal attack positions, opening throttles to maximum power, and watching the target pull away. The experience contradicted everything their training and doctrine promised about intercepting enemy bombers. The Mosquito proved several principles that reshaped aviation thinking. First, constraints breed innovation. The aluminum shortage forced designers to consider materials they would never have explored otherwise. Wood became an advantage precisely because it was the only option available. Second, subtraction can be more powerful than addition. Every previous bomber design had added guns, armor, and crew to improve survivability. Subtracted everything and achieved better survival rates. Third, physics ultimately defeats doctrine. German tactical doctrine was sophisticated and battle-tested, but it couldn't overcome the basic mathematics of power-to-weight ratios. The legacy extends beyond aviation. The Mosquito became a case study in engineering programs worldwide as an example of lateral thinking under constraints. When conventional solutions are unavailable, the answer might lie in completely reimagining the problem. Didn't try to build a better armored bomber. He built something that didn't need armor. The distinction seems subtle but produced revolutionary results. How did a wooden bomber outrun German jets and survive the war? The answer is simpler than the question suggests. Physics defeated doctrine. Weight mattered more than armor. Speed provided better protection than steel plating and gun turrets. Every conventional rule said add guns, add armor, accept the weight penalty, and hope defensive fire kept you alive long enough to reach the target. Ignored conventional rules and trusted mathematics instead. He subtracted weight. He subtracted defensive systems. He subtracted the assumptions everyone else accepted without question. Then he built the airframe from wood, not despite the material's limitations, but because Britain's aluminum shortage forced creative thinking. The constraints that seemed to doom the project actually enabled it. Wood was lighter than aluminum per unit of structural strength. Wood could be worked by craftsmen outside the overwhelmed aircraft factories. Wood created smooth surfaces that reduced drag. The material everyone dismissed as obsolete proved ideal for the design requirements. The Mosquito story is ultimately about having the courage to trust physics over convention. Calculated that 12,000 pounds moved by certain horsepower would outperform 24,000 pounds moved by the same power. The calculation was correct. He predicted wooden monocoque construction would be lighter and stronger than expected. The prediction was accurate. He argued that speed would provide better protection than armor. Combat proved him right. Every expert who laughed at the wooden bomber had to eventually admit they were wrong about every objection they raised. 7,781 aircraft built. Tens of thousands of successful missions flown. 0 structural failures. 0.3% loss rate compared to 8% for conventional bombers. The numbers don't lie. The wooden plane that shouldn't have worked became the aircraft everyone feared, and no one could counter. Furniture makers built a weapon that embarrassed professional aerospace engineers and rewrote tactical doctrine. Simple physics executed courageously beat complex tradition executed timidly. The impossible was just an opinion, proven wrong by an aircraft that dominated the sky anyway.